All right. So I think what we're going to do today, kind of start out talking a little bit about the binomial of Poisson, then kind of go into some review of those problems, and then also do some review of more of the probability rules based off of kind of those of you who responded to that survey. So we won't work through every problem or on one of those at practice exam, but work on quite a few. If you have any specific problems, kind of after we get through kind of the probability stuff, I can kind of work on some of those. Otherwise, the exam is going to be like 18 multiple choice questions and then a couple short answer. So the short answer I would expect to be more of some of the stuff that we've done kind of recently. I know, excuse me, I know those binomial Poisson distributions can be a little bit tough to get entered in your calculator, and so seeing your work there, I can give some partial credit. So those ones will probably be what I would expect the short answer questions to be, is some binomial Poisson distribution questions. That Connect assignment, I believe I have the due date set to be the end of the day Thursday, and then Excel the end of the day Friday. I might and just kind of change that so they're both the end of the day Friday. That way you don't have to kind of worry about mixing those up at all. Give you a little bit extra time, and then hopefully after that, kind of have the weekend kind of leading into Monday, kind of going over those exam reviews. So those practice exams will be very good study materials for what the exam's going to look like. Okay. So I'll add in some questions today that might be good to know. I wrote the exam already, so I might know what would be good to know. But we'll kind of the direction that we'll take. So any questions for me before we get going here? And as far as that formula sheet, I'll print that out and bring that, so you don't have to worry about printing it out and bring it to the exam. Everyone will have that exact formula sheet that's up there on Canvas under the practice materials folder when we start the exam. So here was kind of our general form of the Poisson distribution equation. And I had an example I was going to show you where I kind of set this up as not just a time interval, but you can do intervals over space. I don't want to waste time with that. It's in the slides if you want to kind of go through it, and I'll come back to these in a second, where you can look over like this given space as opposed to a given time interval. So here I'm looking at a volume of liquid. I can see what the average rate is over that interval. So it's not a time interval, but a milliliter now is kind of our spatial interval. And we could kind of set this up the exact same way. So I had this example where, every milliliter on average, kind of our lambda was that we had 10 yeast particles, right? This big vat of liquid that we're trying to make beer with. What's the probability that if I kind of take a sample at random, that I see that it only has 8? So that would be kind of the number of particles I'm interested in finding the probability of, or my X value. We could find these probabilities in the exact same way we've been doing these time interval ones. But now for us, we're only going to do time intervals. So what I'd rather focus on is kind of, here I'll go to practice exam A. I've got this question at the very end, right? So I think I used this example last class. I might change this to the exam, but let's say the number of people struck by lightning every year and killed is what, 3? Right? So I want to know what's the probability, or maybe it's not killed, maybe I got 2 more there. This struck by lightning. So what's the probability that we see less than 2 in this following year? So the main difference between the Poisson and binomial, and I had kind of those 2 multiple choice questions in the slide, but I think there's probably an easier way to kind of summarize it down, is that we're in both situations looking for the number of successes, right? The probability of seeing fewer than 2 successes. The probability of seeing exactly 10 successes. The difference is that with the binomial, it's out of a certain number. So this was the idea that I select 100 people at random. What's the probability 5 out of 100 have to lie? I flip a coin 30 times. What's the probability 15 of the 30 come up heads? So anytime you have out of a certain number, that's binomial. Or you can kind of think about it as, with our binomial, our number of successes are capped. Okay? With a Poisson, we're always looking at a time interval, or you can kind of think about it as it's open-ended. I don't know what number of successes is the maximum. When I think about the number of people struck by lightning in the US, I guess technically I can think about my population is my maximum there. But over this time period, the same people can get struck more than once. I don't know what my maximum value is there, right? There's no cap. There's no how many people out of this many. Okay? So in this scenario, we don't have kind of this cap, this out of this highest number of possible successes we could see. So we're going to treat this like the Poisson distribution. Now, if I want to find the probability x's, or the number of successes is below or above a certain value, I can't just use that Poisson distribution equation once. It only tells me the probability of exactly one number of successes. Okay? So if I'm thinking about here, right, what are all the different criteria that fit that statement of being less than 2? X could be 1 or X could be 0. Right? Now from here, it's just a matter of going back to that general form of the equation. So I think it was, see if I can remember from memory. I think it's this. So I basically use that Poisson distribution equation once. I've got my average rate of 3. I raise it to the power of X. So this first probability I want to find, X is equal to 1. E to the negative lambda over X factorial. I would then add to that. My lambda is still the same. It's just now I'm looking for the probability I see 0 successes. Now, hopefully we notice 1 and 0 factorial actually both end up being 1. This simplifies that a little bit. Anything with 0 power is 1. So you can kind of simplify that. But that's really, once we enter that in our calculator, we should be done. That's the question. Any questions on that process before I add something? So there's two things that both, well, so there's one thing that applies to both the binomial and the Poisson, and then one that applies to the Poisson specifically you can see. So maybe instead, I ask for what's the probability that I see 5 people struck by lightning in the next 2 years. It's not that much more complicated. All we have to do is first convert our average rate to the new time interval we're interested in. Once we have that new lambda, the new average rate for our new time interval, it's exactly what we're doing before. So here, if the average every year is 3, how would I find the average number of people struck in the next 2 years? 6, right? I'm just multiplying that by whatever factor gets me to this new time period. So I think in the homework, it's a little bit more difficult. It'd be something like 31 minutes instead of an hour. So you should have been multiplying by 31 out of 60. On the exam, if I do some type of conversion, I'll make it very easy. The new interval will be like 1 year. So I'll either go like 1 to 2 years or 1 year to 1 month, in which case we just divide by 12 or multiply by 1/12, right? I think the way I set it up is telling you just divide by a factor. So I'll keep it kind of nice and easy going from like 1 month to 1 year, not like 1 year to 1.5 months, right? Or 1 year to 2.3 months or something like that, right? I'll kind of keep it only at 1 units, right? 1 month, 1 year, 1 day, 1 week. Or I might duplicate it, right? Hopefully you could do that, right? 1 year to 2 years, you just multiply your old average rate by 2. Now it's as simple as, let's say I want to find the probability, oh, here it was. I see 5 people struck in the next 2 years. Well, my new lambda is 6. My X value, the number of success I'm interested in finding the probability of is 5. Now it's just a matter of using that equation one time. Okay. Questions? I want to point something out though in this multiple choice question before I show you one more thing that applies both to the Poisson and binomial. So here, if I'm thinking about, the average of the Poisson distribution is just 1. The average number of people I'll see struck by lightning over a year is 2. So 2 is what I was thinking probably of, right? The actual number I was given is 3. 3 people on average get struck every year. That's my average. My Poisson distribution mean or my Poisson distribution average expected value is that lambda. So 3 should be the most likely outcome. So if I'm thinking about this visually, here's my number of successes. 3 is going to be the most likely outcome. And then we said, as we move further from that expected value. Wait, what did I do wrong here? Mess my numbers up. Hold on. Here we go. 2, 1, 0, 4, 5, 6, off into infinity. Okay. So as I move from this expected value, the probabilities decline. So if I want the probability x is less than 2, all I'm really doing is taking the probability it's 0 and adding that to the probability it's 1. Okay. So should this probability be relatively small or relatively large? It excludes the most likely outcome and then the next most likely outcomes. And then a bunch of outcomes to the right. It's only including kind of these 2 outcomes that are, you know, not going to be one of the 3 most likely outcomes. So I should think right away, it's probably something less than 0.5, or it's relatively small. Now, how small, I can't really say. But if I'm just guessing here, I probably can rule C and D out right away, because I know the probabilities that I'm looking for are not going to be one of the 3 most likely outcomes. Now, from there, I can't really make a guess between A and B. Or if I saw something like 0.3 in there, I couldn't really rule that out. But if I'm not including the most likely outcomes, it definitely can't be greater than 0.5. Because if it was greater than 0.5, I mean, sorry, if it was one value is greater than 5, it would make it the most likely outcome. But even kind of seeing 2 of those have a probability as high as 0.5 wouldn't allow for the probability to be distributed enough across those most common outcomes to even make sense. Okay? Now, you know, that's going too far. You don't have to worry about that, because no matter what, you don't just want to make a best guess. You want to actually get the answer, so you're going to have to plug everything in. All right. Another way to think about this is, what if I wanted instead the probability x is greater than or equal to 2? Well, that would include 3 of the most likely outcomes, and then every other outcome to the right. So that probability should be relatively large. Now, I don't want to go through and find the probability x is equal to 2, plus the probability x is equal to 3, plus 4, plus 5, plus 6, because every single time I do that, I'm going to have to use that Poisson distribution equation. So what's an easy way I can find this? Yeah, right. If this is the event I'm looking for, we know that's the same as 1 minus its complement, or 1 minus the probability x is less than 2. Similar to what we did over here. Now I only have to use that equation 2 times and then subtract it from 1. So it makes something that otherwise would look impossible to do on an hour and 15-minute long exam actually doable.
So you would take those 2 right there, solve them and add them together.
Yep.
Subtract them to 1.
Yep. If this is what I want to find. Yep. Yeah. So that's just something that so I just gave this not in context of this example, just an example of something we could do, right? Because if I tell you the average rate over a year is something, and then I ask you for the probability that you see a certain number of successes over 2 years, you don't simply say, I can't do that. Well, no, you can do that, right? If you know the average rate over a year, you implicitly could know the average rate over 2 years by simply multiplying that by 2. Then once you convert that to find your new average, now I can solve with something like some time interval that I wasn't originally given directly what that average rate was. Does that make sense? So why are we doing it? Because that pops up in real life, basically, right? And you might have to convert. You might know the average over a certain interval, but you want to make projections about longer or smaller intervals. Questions on anything else? So we've got some assumptions and stuff, some binomials, some other stuff we can do. The binomial will go up here. Yeah.
Will we have graphs or anything?
No, so I won't make you draw any graphs, but I'm not going to necessarily give you the types of things you'll see is anything you would see on these practice exams. So you'll probably see tables maybe, right, that tell you the probability of seeing of different outcomes for X. Maybe something like this. We kind of did problems like that in class. A contingency table, I can guarantee you'll see. We'll work with that in just a second. And, you know, maybe just some values organized in the table. But in terms of like drawing out the distributions or drawing out graphs, I'm not gonna, there we go, expect you to do anything. Is that what you were kind of getting at?
Yeah.
Okay. All right. So I don't know why there's extra space here, but I'm going to delete it. Just that when I'm scrolling, it makes it easy. So let's say instead I had an example like this where I know the percent of people that have a visual impairment. Okay. And then I select 15 people at random. Okay. So I've got these 15 people. I know that the probability that any one person, if I grab them out of the population, that they have a visual impairment is 64%, or a probability of 0.64. So automatically I should be thinking about, if I'm looking for different numbers of successes here, what's the most I can see? Yeah, 15. I've only got 15 people. So I know that I'm capped. This should be an example where I either see someone have a visual impairment or they don't. And the most I can see is however many people I'm looking at, or my number of trials. The underlying probability that any one person, if I selected one person at random, so instead of n was equal to 1, well, then my probability of success would just be whatever it is in the population. So 17 should be, if I ask you this question in the exam, this should be a very easy question to correct. Okay? If I want the mean of a binomial distribution, and I pull open this formula sheet, now I kind of mentioned this, someone stopped by my office and I kind of, you know, not trying to make this too difficult. You'll notice if you look at the practice exams, it follows the order in which we, like I taught you things in class. And the order of the formula sheet is the order in which we cover things in class. So if you get the problem 20, you should not be using one of these equations, right? You should probably be using an equation that's towards the bottom right corner. I mean, that's not a technical way to know what equation you'd use, but at least you're not going to be way off, right? From there, I even tried to group this together. Some of my lines, I guess, screwed up when I convert it to a PDF from a Word document here. I think the version I have that I'll print out is Word, so that shouldn't be a problem. But you'll notice I kind of grouped these equations by the topic. So here, hopefully we see all these factorials and we say, oh, this is binomial stuff. All right. Here's my assigned distribution. Here's my binomial equation. So we said we could find the mean and the variance of my binomial equation using these pretty simple formulas. Well, for the mean, that was simply n times p. Right. So here, that'd be what? I think it's like 9.6-ish. I might be a little bit off. Should be pretty basic, right? And I asked you for the variance. You should be able to plug it in. All right, sigma squared represents the variance. Just now it's the variance of the binomial distribution. So n times p times 1 minus p. This is going to be what? Something 4 point something. I can't do that in my head, but if you enter that in your calculator, you could reproduce what that variance would be. Okay. Those should be easy points. So I ask you for the mean or the variance or both of a binomial distribution. Here's my binomial equations. Here's what I use.
I got 3.46.
Sounds all right. I might have overestimated a little bit. Okay. Any other questions on that one? Okay. So hopefully that one's easy. Stay on practice exam A. What if I want to know the probability exactly 10 people out of these 15 to have a visual impairment? So this is just to find the mean for the expected value. What I now want to find is the probability of a specific number. Right? So here, what I'm looking for is the probability that X is exactly equal to 10. So I have to use that binomial distribution equation, that probability mass function. But I've got NP, and I now have that X value. It'd really just be a matter of plugging everything into this equation and making sure I can get it entered in my calculator. So going back to the slides, reworking some of those binomial distribution problems, even in the homeworks, making sure you can reproduce those answers. After the Excel is due, so after Friday, Friday at midnight, I'll put up the answer key. So even those binomial ones where you used Excel, you could redo those by hand. And just, I'm only suggesting that to make sure that you can get this in your calculator. I think the easy way to do that is often breaking this down into parts instead of trying to put it all in the calculator at one time. Finding that factorial button, I know if you haven't found it yet. Usually there's a PRB button or you get second math. I highly suggest finding that. Can't find it, please reach out sooner rather than later. But that's all we're going to do, right? So n is 15, so we've got n factorial over x factorial. So this is what I would do if I was taking the exam. I have the formula sheet in front of me. I write down what I was given in the problem, and then looking at that formula sheet, I'm just plugging things in, right? So then n minus x factorial, probability of success, the x power times 1 minus that probability of success to the n minus x, right? Maybe even helps just to write it out so you can see everything. What I would probably then do is do all the math I can do in my head. 15 minus 10 is 5. 1 minus 0.64, even if I can't do this in my head, what, 0.36? 15 minus 10, 5, right? Just simplify things before I go to my calculator. So from here, I would probably break this down into 3 parts, right? Find these 3 different values, okay? Hopefully these will be pretty easy to get entered into my calculator. I'm just taking a number to a power. This one, I'm gonna have to use my factorials. It might become a little bit convoluted, but I could also remember if I don't know, for some reason couldn't find my factorial button, or I gave you an example, I don't know, where maybe these factorials were too large, although I doubt I'm going to do that, and I wrote the exam, so. All right, and 5 factorial. We'll notice everything from 10 on down here would cancel. I could get this entered in my calculator relatively easy. Find that 3rd component, right? So just breaking it down to components just to make the math a little easier.
Will the calculator do that for you?
Yes?
Yeah, just all that math.
Mhm.
You have to sit there on the paper and like all out.
No. Now, trying to remember what numbers I used in the exam. If you didn't have a very powerful calculator, or I wanted to prove a point with it, I might ask you to do something like this, which is, let's say n was 80, x was 2. You try to enter that in your calculator, it won't work. But remember what I said is that we gotta be smarter than the technology sometimes. Right? Just because it can't handle this number and then calculate this and divide it. If I were to just start writing it out, I would pretty quickly see, this is 78. Everything here would cancel, and this would be something very easy I could do. But more likely than not on the problems, you should be able to use that factorial button to handle the numbers. But in practice, you might have to write that out because the calculator can't handle anything over 60 something. Questions on that? So I think the last one is, I don't know, it's a probability we see one.
less than 15, that less than 14 people have a visual impairment, okay? So once again, I just look at, oh.
Let's, before we even start plugging things in, see if we can limit this. So we've still got n is 15. The probability that probably any one person has a visual impairment is 0.64. And now we're looking for the probability that x is less than 14. Now, what's the most likely outcome? We already found earlier that the mean was what? 9.6. So what are the two most likely outcomes? 9 and 10, right? The values on either side of that mean. We can only see discrete, we can only see integer values. So I know that 9 and 10 are going to be the most likely outcomes. So this is where drawing this might help me see, like 9 and 10, or sorry, I said 9 and 10. I wrote down 8. 9 and 10 are the most likely outcomes. And then as I move in either direction, those probabilities start to decrease. Right? Well, here, if I want the probability of being less than 14, that means I would be adding up all these probabilities. So I'm including the two most likely, the next most likely, the next most likely, including almost all of the most likely outcomes I'll see. All right? Or think about it like this. On average, I'll see 9.6 people have visual impairments out of 15. So what's the probability that fewer than 14 have a visual impairment? Well, it's going to be pretty likely, right? That includes all the most likely outcomes as well as several of the others, right? So this probability should be probably pretty close to 1. If I added up the probability of every possible outcome, those will add up to 1. I'm only excluding what values here? 14 and 15. Not only am I excluding those two shouldn't even be very likely outcomes. So if I'm looking here, I mean, C or D has got to be the answer. There's no way it's as low as A and B, right? I'm including the most likely outcomes, not to mention I'm only excluding 2 of the possible, technically 16 outcomes, if we include 0, right? So 15 plus that 0, 16 to come. So here's a ballpark of this. I should cross A and B out right away. Well, now notice A and B are kind of flip-flopped. All right, well, these would kind of add up to 1. Well, why is that the case? Because if I want to go through and solve this, what would I have to do? Take the probability x is equal to 13 plus the probability equal to 12 plus 11 is 10, all the way down to 0. Do you expect me to do that an hour and 15 minute long exam? No. All right. So what can I do? This is just going to be 1 minus the complement. There's only 2 outcomes that would fit this criteria. So now it's just a matter of plugging these into my binomial distribution equation. Once where x is equal to 14 and once where x is equal to 15. I might be even kinder on the exam, and I might even do something like this so that you really only have one value to use. Okay? But for the sake of this example, right, 2. So from here, it's just a matter of plugging our values in and making sure we can get that binomial equation and into our calculator correctly. Now, one thing I'll kind of mention, because it makes things a lot easier, if I was to write this out. No, this is wrong. So let me write this out and then I'll discuss why this is actually easier than it might on the face look. So when I'm interested in finding the probability that all of my outcomes are successes, or one outcome is a success, if I do the math ahead of time before I go to my calculator, a lot of things simplify. So 15 minus 15 is what? 0. Anything to the 0 power is, I can ignore that. 15 minus 15 is 0. 0 factorial is 1. I can ignore that. 15 over 15 factorial. All I really have to put in my calculator is 0.64 to the 15. Then for this one, 1 factorial is 1. I can ignore that. 15 factorial over 14 factorial. Everything's going to cancel except for 15. Or I could enter this in my calculator and it could tell me that the value is 15 pretty quickly. Here I've got anything to the power of 1 is just itself. So what, 0.36 to the 1, I could just treat this as 0.36. So a lot of things would simplify to make this, hopefully a little bit easier even than if I had to use this binomial equation to find something like, I don't know, probability is equal to 10. Okay? So it's really extremely large number of successes or extremely low. A lot of things will cancel and make life a little bit easier. Okay? Questions there? What if I change something or different type of problem like that? All right, so let me think if there's anything else I want to say here. So I can almost guarantee you, I'll ask you to find the probability of one specific number of successes from a binomial example. I can almost guarantee you, I'll ask you about the unit binomial, and I'll probably do something like this where you'll have to use that complement rule. I will also guarantee that I'll ask you something similar with a Poisson, where I might ask you to find the probability of it being below a certain value, right? And I might also expect you to have to change the time interval to then find the probability of exactly a specific number of outcomes or a number of successes. So this would all help. Right? So hopefully you were kind of jotting this down as we went through it. Okay. Any other questions related to the binomial or Poisson before we kind of move on to looking at contingency tables and Bayes equation? All right, so we'll stay on A. I think I like the example on A better. No, I don't. Let's switch over to exam B. Okay. I think this is the one I like a little bit more. Yeah. So, excuse me. That was the newest stuff I did, so I'll erase this. So let's say I give you this contingency table. You'll notice I do something similar on both the practice exams. So it's a pretty good indicator. I'll probably do something similar like that on the exam. All right. So I give you these two events. Now, this one's a little bit different. I'm going to have whether or not someone supports legalization of marijuana or not, and whether or not they're Republican. You can think about these are events and they're complements. So the way that I kind of said you could notate this is being Republican is event R, wanting marijuana legalized is LN. And then if you're in the no column or the no row, that's basically the complement, right? You wouldn't be a Republican or you wouldn't want marijuana legalized. So we said that those total columns, right? How could we reproduce those total columns? Just add.
So for this one, we subtract 0.55 and 0.15.
So how do you produce those totals? You're jumping it again. You're jumping the gun, but you're right. Those totals are produced by adding across the rows or down the columns, right? 0.15 is 0.35 is 0.5. 0.15 plus X should give me that 0.55. So from there, a little bit of algebra, and I can see that X would be 0.4. Okay. Any questions on that? Hopefully, if I ask you to do something like this, this is an easy points in this, and this should be pretty basic. If I left off one of these totals, right? Well, then that should also be easy. You should be able to just add down the column 0.15 and 0.35 to reduce that total of 0.5. Okay. Any questions there? That shouldn't be too bad. So I then asked these kind of in a out of order, so to speak. I'll go over the easier one first, which is 7. Okay. So 7, I want the probability of what? the individual is not Republican and does not want marijuana legalized. So if I see this word and, I should be thinking this is the probability of the what of two events. So union would be the word or. Intersection is the word and, right? My intersection, I'm kind of thinking about the union was this, what looked like a U, intersection is an upside down U, right? So here I want to know what, are they not Republican? Remember, complement just means not, or whatever we're looking at. So RC, our complement, not Republican. And they don't want marijuana legalized. Right? This is our intersection or our aim. Well, if we go up to that contingency table, if I don't scroll up too far, the intersections are just those top 4 less cells, right? Or wherever the row and column heading kind of intersect, that value would represent the intersection of those two things. So for us, we wanted that they were not wanting marijuana legalized and they were not Republican. So it's simple as identifying that one value in our contingency table. If I ask you for the intersection from a contingency table, you just grabbing one of those values out of these top 4 left cells. Which value do you grab? Well, wherever the row and column heading kind of intersect that you're looking for. Any questions on that? So once again, those should be easy. 6, maybe a little bit more difficult. Okay. So with 6, I want what? Well, here I'm going to see, and someone to connect homework assignments, or problems. It would be more difficult than what I'll show you on the exam. So I can guarantee you the way I write the exam, I will make the terminology easy to identify what you are given, right? What you know to be true. How do I do that? I'll use the word given, right? So given that an individual is a Republican, now remember, when we're looking at conditional probabilities, that's that vertical line. What are we given? Well, that's what's on the right-hand side of that line. And then what we're still looking for the probability of is whatever's going to be on that left-hand side here. Given that the individual is Republican, what's the probability they want marijuana legalized? Okay. Any questions about how we identified just what we were looking for there? So whatever you're told is given, whatever you know to be true, that's what's on the right-hand side of your line there. Okay. So if I go to my formula sheet, and I scroll up here, and I look at these probability rules. If I want to find the, oops, there it is, the conditional probability of 2 events, I can rewrite that as the intersection of those 2 events divided by what I'm conditioning on. Okay. So what might help is if you write down what you're looking for, write what your A and your B are, so you can kind of line this up with the formula sheet when you're looking at it. Okay, so I've got A and B, so the probability of A and B here. Well, my A is they want marijuana legalized. My B is that they're Republican. And then they're going to divide by whatever I'm conditioning on. And this is like I'm limiting the space from 1 down to whatever the probability of whatever I'm conditioning on. Or kind of reminds me, I'm dividing by the probability of B here, what's on the right-hand side of that conditional line. So my B is that they're Republican. Once I write out that conditional probability as the intersection divided by what I'm conditioning on, hopefully this is pretty easy. So we go back. What's the probability someone is Republican and wants marijuana legalized, or vice versa?
0.15.
Yeah, right. So how did you do that? You went probably they're Republican and want marijuana legalized, just that 0.15. And then the probability that they're just Republican. Well, here I kind of gave some nice easy numbers, even if you kind of messed up here. But those total columns, or those total cells, sorry, represent the probability of the events themselves, right? The row or the column head. So if I want the probability that they're Republican, yes, the Republican, I go down to that total and get 0.5. Now notice in this one, I kind of had Republican, non-Republican evenly split, so it was a little bit easier. I could have maybe looked at the wrong column and still got the right answer here. But that won't always be the case. So that's what? 0.3? Does that make sense, or any questions on finding that conditional probability? Okay. We'll spend a little bit of time on this. So we'll go to 9 first, if it's easier. Or actually, no, we won't. Sorry, there's something else I want to show you first. Before I forget, which is good, but I didn't forget. So what if I wanted the probability of not wanting marijuana legalized, or, right, not being Republican? So here I want the union of two events. So if I want the union of two events, I've got an equation that my formula sheet reminds me of how I can find that, which is right here. Right? So if I want the union of two events, that's going to be take the probability of each event, add them together, and then subtract out what I'd be double counting, or what's in both of them, or what's the intersection of those two. So here, my A is not wanting marijuana legalized. My B is not being Republican. And the intersection of those two things, I could write in there. Now, once I rewrite my union as these three components, now I'm just following the general form of this equation right here. I'm just writing it out in the context of my example. Well, now it's just a matter of what's the probability someone doesn't want marijuana legalized?
Is this a complement or is it just?
So this would be the complement. So this is where the way I wrote this, you kind of, if you wanted to write this out as, instead of LM complement, you could think of this as LM is equal to no, right? Or Republican is equal to, sorry, not 0. No. So here, what would be the probability they don't want marijuana legalized? Yeah, just go over 0.45. What's the probability they are not Republican? That Republican is equal to no. 0.5. And down to that total. What's the probability they aren't Republican and don't want marijuana legalized? 0.1. Now it's just a little bit of math. So, question like this, asking for a union would be fair game on an exam. Might be a reason why I'm showing you how to do it. So you should be able to know how to use those contingency tables to find unions. There'll be another example that Excel answered to you once that due date is passed. Looking at that problem, let's see how that one's worked through. This is how you start doing these events. Okay. Questions on that? Does anybody remember what's the other easy way I said you could do this? It's not very technical. You want the union of two events, you could just go to the intersection, make an L, and add those up. So 0.35 plus 0.1, X was 0.4, end up adding up to exactly the same as what we found over here, 0.5. It's not a very technical way of finding it, right? The formula sheet won't remind you how to do that. So this might be an easy way to go about it. It depends on what next is about. So I think then we'll jump to number 9, which was, are these mutually exclusive events? So looking at this contingency table right away, you can tell me whether or not these are mutually exclusive. So we said things are mutually exclusive at what? They can't happen at the same time. They're exclusive from each other. You can only see one or the other, you can't see both. So if I can't see both, what's the probability of the intersection? Can't happen, so 0. So the only way that I'll have mutually exclusive events is if I see a 0 somewhere here. We don't have any zeros here. I only saw for x it was 0.4. So right away we know that these can't be mutually exclusive. Their intersection is something other than 0. Or one way to remember this definition of mutually exclusive, no matter what events we're looking at, we're really thinking about that intersection would have to be equal to 0 if they were mutually exclusive. If it's not equal to 0, then we would say they're not mutually exclusive. Well, here we don't have any zeros, so automatically we know that no, these can't be mutually exclusive. And the reason why is because the intersection, right, it's upside down, you represent the intersection, it's not equal to 0. Now, if I want to rule some answers out here, anytime I'm talking about the union, that tells me nothing about, well, I shouldn't say that tells me nothing about if they're mutually exclusive. For the sake of what we're doing, we can't just simply look at that union to determine whether or not they're mutually exclusive. That doesn't tell us the whole story. So B and D don't even make sense because the way that we determine mutual exclusivity is if the intersection is equal or not equal to 0. Then from there, does C make any sense? Well, if they were mutually exclusive, if the answer was yes, then it would have to be that the intersection was equal to 0. So saying yes, they're mutually exclusive because the intersection isn't, that one doesn't make any sense at all. So actually here we're depending to rule out every single answer except for A without even really looking at that chart to see if the intersection was 0. So that's the only one that would make sense for us there. Kind of remembering that definition of mutual exclusivity is the intersection equal to 0. If it's not equal to 0, then no, they're not mutually exclusive. If it is equal to 0, then yes, they would be. Yeah. Any questions on that? All right, then we'll go back to 8. It's a little bit trickier. But we're going to use, just to make this easier, we're going to use what we already did over here. Okay. So we're asked here, is wanting marijuana legalized and being a Republican independent of these independent events? So the real definition of independence is you're looking to see, actually, what did we do over there? We did LM given R. I want to try to reuse this and then make it more. Remember, whatever is on the right-hand side, that's what you're given. What's on the left-hand side is still what you're looking for the probability of. So we would call this the conditional probability of LM, or wanting marijuana legalized. We would say that events are independent if that's the exact same thing as the unconditional probability of LM. Right? So you can kind of think about whatever events you have here, what's on the left side of that conditional line, you should be comparing to that same event here where you're not conditioning on it. You should not be doing something like this. Because now you're comparing the conditional probability of R, or being a Republican, to the unconditional probability of wanting marijuana. Well, that's not the definition of independence. The definition of independence is the underlying probability of some event is the same as the probability of that event occurring even after you were given that additional information. Excuse me. So if this equality holds, we'd say that these are independent events. If this equality doesn't hold, we would say no, they're not independent, they're in fact dependent. Knowing that one event has occurred will change the probability of the event that I'm looking at. Well, how do I actually check this? Well, how can we rewrite the conditional probability? We did it over there. We took the intersection of these two events and divided by what I'm conditioning on, right? That's exactly what we did over there. So we've already found this conditional probability is 0.3. Is this equal to or not equal to the probability of just without conditioning or anything that someone wants marijuana legalized. So we scroll up. The probability they want marijuana legalized would be 0.55. All right. So if we come back down here, plug in 0.55. You can see that they're not equal to each other. So we would say that we do not have. I guess I shouldn't have put 0.55 in here. Sorry. Jump the gun. So if that equality doesn't hold, we would say no, they're not independent. So we know there it's going to be either A or B. From there, we should rule out anything where we're not comparing the event that are the events on the left side of our conditional line to the unconditional. So here, we know the answer is no. We're comparing the conditional probability of being Republican to the unconditional probability of wanting marijuana legalized. That's not going to tell us anything about independence. If we compare the probability of being a Republican, a conditional probability of being a Republican, to the unconditional, and they aren't the same, well, then that would tell us that they're not independent events. So if that equality doesn't hold, and we say no, they're not independent, that's because this equality didn't hold. These two probabilities were not equal to each other. Now I used what we had already done to kind of show that even if you were to write it out this way, you were to solve for independence, and this tells you wanting marijuana legalized and being Republican are not independent events. They depend on each other, or the probabilities at least depend on each other. Well, knowing that being a Republican, being a Republican and wanting marijuana legalized are independent events, you could have checked it the other way as well, which is look for the conditional probability of R and compare that to the unconditional probability of R. So you can check it one way, but as soon as you check it, both ways will either tell you they're both independent or not. So even though we checked it, seeing if the unconditional and conditional probability of LM or wanting marijuana legalized are the same, that would inherently tell us that this conditional and unconditional probability of being Republican can't be the same. So you could have started out, you could have checked this. We already had some previous work done, which is why I kind of set it up this way, because we didn't have to kind of re-solve for that conditional probability. But no matter which way you solve it, it should be just kind of fun both that they aren't independent, right? So the answer should be no. Okay. Questions there? You also could have ruled out one of these. So which one could you rule out? If they were in fact independent, what would have to be true? So if the answer was yes, they're independent, and you said it was because those probabilities, the unconditional and conditional, weren't the same, that doesn't line up. It's either yes, they're independent because the conditional and unconditional probability is the same, or no, they're not. Sorry, no, they're not, because the conditional is not the same as the unconditional probability.
So C wouldn't even be possible because they have to.
Yeah, C doesn't make any sense at all. It doesn't line up with the definition of independence. Yeah. Yeah, so if we're looking at this, we could have ruled A and C out, just matching up. If they're independent, they have to be equal, and then the other one we could rule out because we weren't even comparing the conditional and unconditional probability. Yep. All right. Any other questions on those before we continue?
You may have said it. How many questions are on the front?
So the 18 multiple choice, I guess it depends on how you count it. 2 short answer, they might have a couple parts to them, like an A and a B. Yeah, roughly 20 questions. Like I said, if you want to count those short answers, a couple, maybe 22. Okay.
And can we use our formula sheet on the test?
Yeah, so what can we have in the exam? Bring a calculator for sure. Preferably not in your phone. I had someone ask me if they could do that. I said no, because if you forget your calculator, you have to use your phone. You're gonna have to raise your hand every single time. You'll take your phone out and have to walk over and watch you use it. I don't think you want to do that, right? So find a calculator, bring that, something to write with, pen or pencil, doesn't matter. I'll print the formula sheets out and give them to you as we start the exam. So you'll have the formula sheet, and I'll also bring some extra paper if you want some scrap paper to write on.
I'm sorry, can you repeat? You said it's 2 short answers and how many?
Yeah, so 18 multiple choice. So it looks similar to these, where the last questions will instead be short answer.
Alright.
So I can give some partial credit if you set up those binomial, basically telling you it's gonna be binomial and Poisson distribution equations as a short answer, because I know that it's kind of difficult. If you can get those set up correctly, I want to be able to give some more partial credit for those. All right. All right, so you got one last batch of questions I want to go through, which is a Bayes theorem example. Try to go over this relatively quick, so if we have a little extra time and there's a specific problem, somebody had a question on it, they were looking at a practice exam, you can ask me. So I'm going to tell you how I would approach these. Now, this is not technically, this is more of like a study tip or an exam taking tip. I told you already, the flow of these exams follows the flow of the class, right? And you'll notice the practice exams are pretty similar in the sequence that they ask questions. Things are a little different, like within 1 or 2 questions, but for the most part, early on, I give you a contingency table. I ask you for a conditional probability, right? If I give you a bunch of information like this, all right, or I give you some kind of story problem, and I ask you a couple probability questions, the second conditional probability you find in the exam will probably have to be using Bayes' theorem. It's not the most technical way of knowing when to apply it, but kind of the second, right? Once you get down towards the middle of the exam, you might see a question pop up where it's a conditional probability. You have to use Bayes' equation. We'll eventually get to that, but I'll kind of prove to you that, or how you can figure it out by not just kind of thinking about where it's at in the exam as well. So if you're given a bunch of information like this, you'll probably then have like 3 questions, right? Maybe only 2 if I'm feeling nice, 2 or 3 questions related to this information. So what I would start out as is just writing this out. Okay? Write out what you're given. So who cares about the first sentence? Manufacturers claim that the probability of drug test shows a positive result, given that an athlete is using steroids, is 0.95. So what are we given there? Well, we're given that they're using the probability that the test comes back positive that they're using. And here's where, if you look at the other practice exam, it's like, are they lying or not? And does the lie detector test detect their lying? I would always write out kind of my outcome of the test. Like the test is equal to this. In this case, it's easy because it's like the steroid test, right? Or the drug test is equal to this or shows this. But it's just a way to kind of differentiate between the outcome of your test and what the underlying states of nature are. Just some notation help there. The next thing I'm told is what? The probability the drug test shows a positive test result given the athlete is not using. So given that they're not using, the probability I see a positive test result is what? 0.01. I forgot to write down the 0.95 earlier. A recent article suggests the probability, if I don't have any information about this athlete, the probability if I selected one at random that they're using steroids is 0.15. 15% of all athletes are using steroids. Huh? So those are the 3 things I was given. Any questions on that? So the reason why I wrote this right here were my givens. And that's why I know that I would put those on the right-hand side of that vertical line. So you don't have to necessarily do this. In fact, the first few problems we worked through, I can't remember if it's this exam or the other. We may not need to do the next step I'll show you. But the next step that I'm going to show you allows you to answer any question I could ask you. So I'm showing it to you for a reason. Okay? So I am given 3 probabilities, but I inherently, knowing these, will also know 3 others. So if I know the probability someone's using, what's the probability of the other state of nature? Or that they're not using? 0.85. All right, when I add up the probability of the 2 states of nature, they have to add up to 1. If I then think about, okay, given that the individual is not using, what's the probability the test comes back negative? Well, given that someone's not using, the test either comes back positive or it comes back negative. So if I'm not using steroids and there's a 1% chance that my test is a false positive, what probability would it be that it correctly identifies me as not using? 0.99. Because when I condition on the same state of nature, you can almost think about it as I'm now just looking at one person who's not using. Well, the probability they get a positive test result is 0.01, the probability they get a negative test result is 0.99. We've got no inconclusive tests in our examples here. Okay. And then up here, similar kind of idea. If I'm now looking at people who are using, well, the probability that they're using, given that they're using, that they see a positive test result is 0.95. Given that they're using steroids, the probability that it doesn't correctly identify them as using and show the negative result would be what? Yeah. And the reason why I wrote this out, you're conditioning on the same states of nature. Here are my two states of nature. These rows have to add up to 1. This is where we said we could also do probability trees to kind of remember that. But if you're given these 3 probabilities, you'll inherently know these other 3 as well. Any questions on that? You can't read something I wrote. I get that I'm running out of room a little bit here, so yeah.
What was the answer to that one?
Here,
Yeah.
0.05. No. Any questions on that before we keep going here? All right, so the very first problem is, what is the probability of what? That they're using steroids and I get a positive test result. And think of this as my event A and my event B. How can I solve for the intersection of 2 things? Well, I don't have any intersections here. I've got a bunch of conditional probabilities. If I look at my formula sheet, I can find the intersection by taking the conditional probability times what I'm conditioning on. So here I've got my A and B. I'll take the conditional probability of B, right, conditioning on A. I'm just following that general form of the equation up there. Excuse me, and I'm going to do this in 2 lines. I'm then going to multiply, not to confuse you, I'm not dividing here, I just ran out of room. I'm multiplying by the probability of A or whatever I'm conditioning on. So if I looked over there, what's the probability that the test comes back positive given someone's using? What's the probability that someone is using? It's as simple as that. So by using that kind of multiplication rule, I'm given these conditional probabilities, I can work backwards and find what that intersection is. Okay. What if I wanted the probability someone's not using and test positive? It should not be too tough, right? So what's the probability that they're not using and the test comes back positive? Well, now I've got just different events. I can write out my conditional probability. So B, which is that the test comes back positive, given my event A, so I'll move out of the way here. That was that they're not using. And then I multiply by the probability of what I'm conditioning on for my event A. That was just from that formula sheet once again. It's basically the same thing as the previous problem. We just changed the event we were interested in, or changed the state of nature from using to not using. Those ones should be pretty easy too, right? Given that they're not using, what's the probability the test comes back positive? Have that over there. 0.01. What's the probability they're not using? 0.85, right? Oops. Simple as that. Questions over either of those. Now, on the exam, what I might be more likely to do, these ones are pretty easy. I might be more likely to do something like this.
Are these legit numbers? Like was.
I tried to grab them roughly. I think this is probably old now. I think this, these are like estimates prior to, the drug and like, they impose some harder sanctions, right? But these test numbers are fairly accurate about what they would be. Well, this is gonna be 0.085, right? And this is gonna be. There's a 9% chance that. And we're not. No. Yeah, if you don't have very accurate tests, I mean, if you're talking about, when I say very accurate, like very, very precise, like you need like 99.9% probability. Okay. So these are our intersections. If I then wanted to find some, or sorry. I was gonna make a point. I might change to something like this, where I want to look at the negative test result because I wasn't directly given those conditional probabilities. So that would be a question like, where now I'm looking at this and I'm like, oh, okay, now to get this conditional probability, I had to do a little bit of extra work. I kind of had to, know that when I condition on the same state of nature, the two probability or the two outputs of the test, those probabilities have to add up to 1. So then I had already found that though, if I ahead of time solve for all those unknowns, and now I just got a value from it. Probably the hardest question, or much more difficult question, is 13. Okay, so does everybody have this here? Can I erase this? I want you to leave those numbers up there. Okay, so what am I looking for here? Given that the test comes back positive, what's the probability that the person is actually not using? So I can kind of think about it as, I'm going to see a certain group of individuals who get a positive test result. Of those, some of them will get a positive test result and not be users. Some will have a positive test result and will be users. So that's essentially what I want in my denominator. Right? Like all the people that get a positive test result should be in my denominator. I can break those up into 2 groups. And then out of all these people, I want to know what's the probability that they got this positive test result, or sorry, given that they got the positive test result, they were not using. So I'll take like the number of people who got a positive test result who weren't using, divide by the total number of people who got a positive test result. If I go to that formula sheet and I try to use my basic multiplication rule, right here, where I rewrite my conditional probability as an intersection divided by what I condition on. So let's say I try to do that, and you don't have to write this down necessarily. I'm going to erase it pretty quick. All right, so I'm just taking my events and writing out the general form of the equation. Do I know either one of these? Well, maybe I know one of them because of previous work, but do I know the probability the test result just comes back positive? I don't have that at all. Right? I've got a bunch of conditional probabilities. So if I write out this conditional probability and I have probabilities that I don't know, and it's kind of in the middle of the exam, probably a pretty good indicator, I'm going to have to, use Bayes' equation, right? Which is down here. This is where we kind of could rewrite things. We're substituting equations in. We could eventually get into this. The best way to approach these, right? S and E over your 2 events. Like I wrote out the probability of what I'm looking for. So the numerator is what? The probability of my state of nature, so that they're not using, times the probability of E given my state of nature, right? So the probability the test comes back positive given that they're not using. And for the sake of space, well, I'll write it out. But notice that first part of your numerator, the first part of your denominator is always the same as your numerator, right? It's the exact same thing. So I'm basically just writing out the probability of S, which was not using. And then the exact same thing, E given S. So these two kind of represent the number, you can kind of think about it as they represent the number of people who were not using and got a positive test result. Now, the second group of people that we'll want to have in our denominator is the probability of S complement. So everybody who was using, and then given that they were using, or given that second state of nature as complement, what's the probability we see this positive test result or this outcome? Yeah.
Can you cancel out the, no, you can't do that?
No, so it's but if I do something like this, if I try to cancel this out, it's not 2/3, right? This is actually 2/4. Okay. So because I'm breaking the denominator down into components, it can't cancel anything out. But it's not an uncommon question. It's a valid question. So at this point, it's a matter of plugging things in, right? What's the probability they're not using? We have it over there. What's the probability they were using? Given that they weren't using, what's the probability the test result came back positive? I've got that over there, all right?
0.01.
Yep, 0.01. Right, these are my false positive rates. And then given they were using, what's the probability the test came back positive? If I'm remembering correctly, you guys can see it was a 0.95.
Mhm.
So now it's just. So it's what? 0.085 divided by 0.085, no, not 0.085. 0.00, right? And then what's ended up being, I forget what that being out somewhere. Anyway, it's telling me out. What does this end up being if I get the center in?
0.1425
1.45.
for the other part.
Oh. So then this would be. We've got fairly well. Everybody wants that one. Just gonna stand here. Okay, you guys.
0.563.
So we go back. Hopefully that's one of the answers.
0.005.
Yeah, if I round it to the third decimal, 0.056. Yep. Okay. Questions on that process? Like I said, I just think it helps writing it out in the context of your example. Might take a little bit of extra time. So if you know that you're having trouble with those and you know it takes you a little longer, maybe save that one for the end, right? Try to tackle the ones that you can kind of work through it without as much problem first. Kind of make sure that time is an issue. I don't think time should be an issue. I've given exams like this usually with 50 minutes. So we'll have a little bit of extra time for the whole hour 15. In fact, maybe I'll stick around 5 or 10 minutes later if you want a little bit of extra time. No one's coming into this room after we are. So depends on how long you want to hang around on Monday, I guess. Yeah.
You said that one of the practice tests on here shows like how you.
Yeah.
Like a legit like that.
Yep. So if you look at the practice materials, the answers where it says answers, those are just identifying the multiple choice answer that was correct. The ones that say detailed, I kind of show you what that intermediate work would be. It's not the best, right? But it gives a pretty good indication of what formula was used, what values were used, and how the actual correct answer was found.
Questions about like Excel?
Yeah, such a good question.
Like what?
Yep. So I won't ask you any, if you look at these practice exams, you'll notice I ask you nothing about Excel functions or how to do things in Excel. So I won't quiz you or exam you, I guess, on anything related to Excel here. So you don't have to kind of worry about anything there. Yep. Nope. Today's the points that you'll get from today is hopefully that you better understand how to get points on the exam. And I can tell you from previous data, there's a strong positive correlation between showing up on a review session and performance on the exam.
And exam is Monday, correct?
Yep, Monday in class. Like I said, I'll try to get here a little early. We could even get going a little bit before 4, if you guys, are here and kind of ready to go. Any other questions?
Monday at 4?
Monday at 4.
Double check.
Yep.